Good afternoon, all. Hello. Can you hear me? All of you?
Yes, sir.
Okay. 12 students attended out of 23. Okay, we will start the class. So far we've seen about transistor, the working model, the constructions, and the three types of configuration. And in that three types of configuration, we've seen three types of region: active region, cutoff region, and saturation region. And then the first configuration is common based. So base will be act as common for both the input side as well as the output side. And so in that the current amplification factor alpha is found. So alpha is equal to IC by IE. Output current is the collector and input current is emitter. And the second one is common emitter configuration. In that emitter will be act as common for both. And in a common emitter amplifier, the output is the collector current and the input is base current. And usually, so that amplification factor is denoted by beta, and beta is always greater than, I mean, in the range of 20 to 200. It will go beyond 200 also, up to 500 it may go. And if you see the current amplification factor of common base, the amplification factor is almost equal to 1 unity, so less gain. So amplification factor is nothing but the gain, how much I can able to improve. And so that we seen, and we seen the input and output characteristics of both the configuration. So how to draw the input characteristics and with respect to what is the voltage and what will be your current. Similarly, the output characteristics also. Okay. And now we are going to look at the common collector configuration. So in that common collector amplification configuration, the collector will be act as a common. It will be grounded. So common means it will be grounded. And if you look at this, the input is similar. It is a base only, and the output side is the remaining terminal is emitter. So output is emitter. Okay. And here the two diagrams are shown. So one is for NPN transistor, which is available in your left hand side, and your right hand side the PNP transistor configuration is shown. But the configuration is same, common collector only. So collector will be grounded. It will be common for the input signal to the output signal. Okay. And the collector, common collectors, is also called as emitter follower. Why? Because the emitter will follow what is the current is flowing in the basin and the collector. So that's why they named it as the emitter follower. So common collector is also called as emitter follower. Okay. And and if you look at this, so we know that so normally the collector base should be a reverse bias and emitter base should be a forward bias. And if you look at this, the base and the emitter. So base is I'm giving a positive potential and the emitter is given a negative potential in a left hand side diagram, and we know that it is a NPN. So N is nothing but emitter and P is a base. So base I'm providing a positive and N I'm providing negative, so it is always a in forward bias condition. And if you look at this collector, so collector will be at a reverse bias condition with respect to the base. Collector base junction is always a reverse bias condition. Okay. And output will be taken from the collector to emitter. Okay. and here the amplification factor is represented using the gamma. So actually totally three amplification factor, current amplification factor. Why? Because each and every configuration, the input and the output is changing. So if you look at the first one, common base, so output current is collector current and input current is emitter current. So it is denoted by alpha. If you look at the common emitter configuration, the output is collector current and the input is base current. So the ratio of collector current to the base current so is represented by beta. So here also the input is changing. If you look at this common collector, the ratio is nothing but comparing with the emitter current with respect to the base current. Why? Because collector is grounded common. So output current is emitter current and the input current is base current. So the amplification factor, otherwise they used to tell us gain, otherwise it is denoted by gamma. For common collector configuration is IE by IB. Okay. And so in a common emitter configuration, the current will be equal to your common emitter configuration. Why? Because here the IE is always almost equal to your del IC. So IB is very less value, so I'm not considering that one. Okay. In last previous case also, if I found the IE, look at this statement. At the end of this, I calculated the IE. It is also equal to your IC. So IC or IE is equal to IB by 1 minus alpha plus ICB or leakage current by 1 minus alpha. This is what we found in last expression in common emitter. And let's see here in order to check the current. So what is the current for common collector? So before that, we have to find the relationship between the alpha and gamma and as well as the beta also. So we will find the relation. Why? Because if you know about alpha and you can able to derive the gamma or beta with known value of your alpha. Okay. So here what is the gamma? Anyone? So what is the gamma equation? What is the gamma equation?
1 by 1 minus alpha.
1 by no. So don't go that one. I'm talking about this equation. Base equation is so here the basic the basic gamma equation is del IE by IB. So that is what represent here. And you know the alpha equation. So alpha equation is the output current for the collector with respect to the input current of the emitter. So alpha is equal to del IC by del IE. So now I want to show the relationship between your alpha and gamma. So here let me take the total current. So total current in your circuit in every transistor, the total current IE is equal to IB plus IC. So keep on remember this equation. So you will use this equation for every relationship in order to find every relationship. This is the base equation. So IE is equal to IB plus IC. So always the emitter current will be equal to your the base current plus the collector current. Okay. And in this equation, I'm just rewriting in with respect to change in emitter current. So I'm representing using a del IE is equal to. So surely if it is the collector current is changing means it denoting that the current which is passing out to the base additional to that the current which is passing to the collector also changing. Is it right? So suppose if I keep a less base voltage, so collector current will be also very less. So that will be equal to your emitter current. If I improve the base current, and surely there will be a improvement in the collector current. So already we discussed about the electron flow. If one electron is coming crossing the base junction and recombining the sense, remaining 99 percentage of the electrons will move across the collector junction. So it representing, so 1% of current is flowing through the base means 99 percentage of the current will flow to the collector, and your emitter will be 100 percentage. Thing is, if I improve, I mean the base current is much more. So suppose it was improved in the sense, surely that much current will be drawn from the collector. Why? Because there is a link between your base and collector current with respect to the emitter. So for example, if 1 milliamps, so if base is the input, 1 milliamps of your current I'm flowing to base means from collector to emitter, for example, take it as a 100 milliamps. Okay, suppose if I am making a current flow of 2 milliamps in a base means surely there will be a change in your collector to emitter current. So that will be equal to your 200 milliamps. So if 1 milliamps is passing to base, if and collector current will be 100 milliamps means if 2 milliamps I am passing through base, the current will be improved to 200 milliamps. So likewise. So that's why here I am representing a del change in emitter current is equal to your change in base current and addition to the change in collector current. Okay, so if I want to write the equation with respect to I, so del IB I kept here there, so that del IC will move to left hand side. So the equation will become del IE minus del IC. Guys, this equation is very simple, right? No need to write it, right? Because it is not a complex derivation. If it is a complex derivation, I will write. So for it is a very simple derivation, a small derivation. That's why I'm projecting. Is there any problem? Can you able to understood?
Yes, sir.
Okay. If facing any difficulty, just inform to me. Okay. So if you can't able to understand the derivation, I will explain again. Otherwise, I will write. Okay. And so I'm going to substitute this IB. So I del IB is equal to del IE minus del IC. I'm going to substitute this equation in your gamma equation. So why? Because gamma is equal to del IE by, in denominator I am representing del IB. So I'm going to replace that IB del IB with your del IE minus del IC. So if you look at this equation, now the gamma equation will become del IE by del IE minus del IC. Okay. Now, so what I'm going to do in the sense, I'm going to divide that equation, the numerator as well as the denominator using del IE. So if I divide it by del IE again, so numerator also already having del IE, I'm going to divide it by del IE. So the equation become 1. It will cancel each other. And if you look at the denominator, so there will be two equation. One is del IE minus another is del IC. So if I divide the entire equation with del IE, so the first will become cancel each other and it will become 1, and minus del IC by del IE is denoted by alpha. So I'm replacing that equation with alpha. So what is the relation between alpha and gamma? So gamma is equal to 1 by 1 minus alpha. All of you understood this relationship? Is that clear? Is that clear, all of you?
Yes, sir. Clear, sir.
Okay, only one are responding always. Okay. And next equation. So do you remember the first equation? Do you remember the first equation? So IC is equal to alpha E plus ICBO. So alpha equation is IC by IE, and I'm adding the leakage current. So the equation is IC is equal to alpha IE plus ICPO. Okay, and you know the base equation, I is equal to IB plus IC. That is a common equation. So in that I'm going to substitute the value of IC. Okay, so in that equation I is equal to IB plus IC. So in the place of IC I'm going to substitute alpha IE plus ICBO. So in a second line they're just substituting, so that here if you found there will be IE in left hand side as well as alpha IE in right hand side. So I will combine each other, right? So I'm taking alpha IE to left hand side. So you may get the equation like IE minus alpha IE. So IE are common. So I'm taking the common IE outside. So your equation will become IE into 1 minus alpha is equal to, so what is your remaining equation? So remaining is IB will be there plus ICBO, leakage current will be there. Okay, and I'm making that I 1 minus alpha to your denominator. So the IE equation, current equation is nothing but equal to IB by 1 minus alpha plus ICBO by 1 minus alpha. Okay, so this is your emitter current equation, and this I can able to use it for the collector current also. So I will rewrite the equation IE is equal to IC is equal to, why? Because IE is equal to IC, both are common. Moreover, both are common, so I am making IC is equal to IE is equal to IB by 1 minus alpha plus ICBO by 1 minus alpha. So this is the current equation. So expression for the carbon collector configuration. And already we know the equation, the relationship between beta and gamma, we already derived, right? So that is what written here. So beta is equal to alpha by 1 minus alpha. Okay, and I'm just adding 1 to left hand side and right hand side. So the equation will become beta plus 1 is equal to alpha by 1 minus alpha plus 1. Can anyone simplify this equation? Simplify the equation. How you will simplify? Anyone tell? So beta plus 1 is there is equal to alpha by 1 minus alpha plus 1. I want to minimize this equation. Can anyone simplify this? Anyone?
Sir, and the one minus alpha is going to that side, sir.
In the sense, I want to make it a common denominator for alpha by 1 minus alpha plus 1. So what I want to do now to make a common denominator, I want to multiply that 1 minus alpha to your 1. Is it right or not? Yeah. So if I multiply with 1 in, so the equation will become, in a numerator I will tell, listen carefully. So it will become alpha plus 1 minus alpha whole divided by 1 minus alpha. So in a numerator, alpha is there, minus alpha is there. So it will cancel each other. So your output, I mean, the final expression will become 1 by, in denominator, 1 minus alpha. So now the relationship between beta and alpha is, I am rewriting as beta plus 1 is equal to 1 minus alpha. And we know what is 1 minus alpha. So 1 minus alpha is gamma, right? So now what is the relationship between alpha and, sorry, beta and gamma? What is the relationship between beta and gamma? So gamma I know 1 by 1 minus alpha, and beta plus 1 you know 1 by 1 minus alpha. So what is the relation for beta and gamma? What is the relation? What is the relation, ma? Guys, what is this? Beta plus 1 is equal to 1 by 1 minus alpha. Gamma is equal to 1 by 1 minus alpha. Then what is the relation between beta and gamma?
Same, sir.
Same. So gamma is equal to 1 plus beta, right? Gamma is
Yes.
equal to 1 plus beta. So that is a final expression. So look at this. Here the alpha and gamma relation is gamma is equal to 1 by 1 minus alpha. So that the gamma and beta relation is gamma is equal to 1 plus beta. So that is the relationship between alpha, beta, gamma. So you can write the entire expression. Um, so alpha and beta relationship is alpha, sorry, beta is equal to alpha by 1 minus alpha. And what is the relation between alpha and gamma is gamma is equal to 1 by, sorry, gamma is equal to 1 plus beta. Okay, so that is a expression you have to write. Suppose if they ask a relationship between alpha, beta and gamma, so everything you have to derive. So okay, so this is just a comparison, and input and output characteristics are also same. Similarly, how you what you studied, the same only input and output characteristics. Only thing is the input will be your emitter. So input will be your, sorry, input will be your base, and output will be your emitter. Okay, so collector is common, so that is the difference. You have while plotting the graph you have to change. So in a common emitter and common collector, input characteristics are almost same. Why? Because input is base only. Okay, and the output characteristics is, in a common emitter I will calculate the current of your collector, but in a common collector I will calculate the current of your emitter. So that is the difference, and remaining all same. And here I'm comparing the input resistance, output resistance, and the gain, current gain and voltage gain, and some application also are given. So it's a comparison chart. So look at the input characteristics. So input resistance, first one is very low for common base and low for common emitter, and for a common collector input resistance is very high. Can you able to tell anyone why it is very high? Why common collector resistance, input resistance is very high? Why the common collector input is resistance is very high? Guys, I told that can anyone tell which is heavily doped? Whether emitter is heavily doped, or collector is heavily doped, or base is heavily doped?
Emitter is doped, sir.
Emitter is heavily doped, correct. So if it is heavily doped, the resistances will be higher or lower? Resistance is higher or
Highest.
lower? Higher. No, doping
Because
means what is doping process?
adding
Adding impurity.
impurity, sir.
Impurities means I am making more number of free electrons, right? So adding impurity
No.
is nothing but, see, actually normal semiconductor, the free electrons is very high, sorry, very low. One or two will be there. Free electrons representing conductivity. More free electrons, more conductivity. So for a conductor, like a metals, we having a more number of free electrons. It will conduct very efficiently. And if you go for insulator, there is no free electron. So conductivity is very poor. It representing high resistance. And if you semiconductor, it is partially conduct. So it representing the number of free electrons is very few. And adding impurity means I will make a more number of charge carriers. So if it is n type, in the sense more number of electrons will generate. So more number of electrons means the resistance become lesser. Okay, and if you look at this common base and common emitter, so surely there will be a emitter at the input side. So if you go for the first one, common base, I'm going to calculate the input between your the base and along with your emitter. So input side. Okay, and if you go for the common emitter configuration, emitter will be in ground, and I'm going to calculate the input from your base. So base to emitter resistance is very less. And if you go for the common collector configuration, I'm going to calculate the resistance with respect to the base along with the collector. Here emitter is not available. So that's why collectors having moderately doped when compared to that. So collector is moderately doped, emitter is heavily doped. So collector having high resistance, emitter having less resistance. So that's why the input resistance for common collector is very high. Okay, and if you go for output resistance, so output resistance, wherever the collector is there, it will be very higher. So if you look at this output resistance for common base, I'm going to calculate the output resistance from collector with respect to the base. So it's very high. Okay, and if you go for the common emitter, I'm going to calculate with respect to collector and emitter. So that's why it is high. Okay, and if you go for the common collector configuration, I'm going to calculate the resistance with emitter with respect to the collector. So emitter is presenting, that's why the resistance is low. Okay, so wherever the emitter is available, resistance will be very less. Okay, and look at the voltage gain. So voltage gain, they given a typical value. So for a common base, the voltage gain is 150, and common emitter, the voltage gain is 500, and a common collector, it is less than 1. Okay, so voltage gain representing output voltage with respect to input voltage, and so far we found the current gain only, and the voltage gain here they are giving. So common base having a moderate voltage gain, common emitter having very high voltage gain, and common collector having very less voltage gain. Okay, and later we'll see the application. First go to the current gain. So current gain for common base, I told it will be less than unity. Okay, so the current is gain is not available, right? Whatever I'm giving an input, same output I am getting. So gain is not there. So they represents there is no current gain. Even I am giving 100 millivolt, I am getting output as 99 millivolt. It is not even improved 1%. So there is no gain at all. And if you go for a common emitter, the beta value is, I told 220 to 500, the beta value. So it representing 500 times it will improve the current from your input. See, it will improve the output current with respect to your input. Suppose if I'm giving a 1 millivolt to your, sorry, 1 milliamps to your input, output will be 500 milliamps. So the gain is 500 by 1 is equal to 500. So gain is 500, uh, very high. And if you go for the common collector, it will be somewhat, it is not less than 1, and it is not more than your common emitters. It will be available between the common emitter and common base, so it is appreciable. Okay, and if you look at this application, for high frequency application, I will use the common base. So at the device which wherever I am using the high frequency, for example satellite communication and microwave communication, I will use the common base configuration. Okay, and if you look at this common emitter, it will be used for audio frequency application. So audio frequency application means like a TV having amplifier inside. I'm increasing the volume, right? So audio, and as well as the home theaters. So wherever the volume is you are increasing, so that those are nothing but audio application devices. Okay, so in that common emitter configuration will they will implement. Okay, and if you go for common collector, it's used for impedance matching. Okay, so what is the impedance matching? In the sense, um, suppose I'm connecting two different device. One device is providing some power or a signal to the another device. The another device want to accept, and in transferring there won't be any disturbance. Why? Because I am going to transfer using the cable or a wires. So if wire is not properly connected and wire having high impedance representing the resistance which is available inside the wire, if it is very high means I can't able to deliver what I want to deliver to the receiver. Okay, so impedance matching is making the two device and to make the power transfer perfectly without any loss. Okay, so for that I will use common collector configuration. Okay, mostly we will use the common emitter configuration. Why? Because it is having a very high voltage gain as well as the current gain. Okay, if you go for the common base, the voltage gain is okay but current gain is very less. If you go for common collector, voltage gain is less and current gain also moderate. So I preferred common emitter configuration for majority of application in order to do the current amplification as well as the voltage amplification. Okay, so all of you clear about this comparison? Any doubt is there, all of you?
No, sir.
So transistor as an amplifier in common emitter configuration. So common emitter configuration, I will make a transistor to act as an amplifier. So amplifier means increasing the signal strength. So example audio. So audio amplifiers are there like home theater speakers. So speakers having the volume button. So if I change the resistance, that is called a load resistance. So if I change it, I can able to change the gain. Okay, so here if you look at this, I'm going to give a signal. Can you able to see one circle is there in that one sine wave I'm giving across the base IB? Can you able to see that in the diagram? All of you look at the diagram. All of you look at the diagram. So you can able to see here. So there only I'm going to give you a audio signal which is having a very less voltage. Okay, and based upon that voltage I will drive the base current, and that base current will try to improve the collector to emitter current. So this is the actual operation. So if I'm having very less base voltage, so on the time so for example listen, if I'm giving a zero voltage, on the time base doesn't have any sufficient voltage to make the transistor to switch on. So on the time the output will be very high. uh, um, Guys, look at the input is base with respect to the emitter, and output I am connected across your collector to the emitter with your output voltage, that is your biasing voltage. It is called VCC, and look at that. So VCC for example make it at 12 volt. Okay, and I am going to give the base current. So suppose if I am providing any base voltage and on the time only the transistor will become on. So if it is on means the current flow will occur from collector to emitter. If current flow is occurring, what will be your output? Output will be less, or output will be very high? Output, if the current is flowing across a two terminal, the voltage will be less or voltage will be high? Hmm? Voltage is less or voltage is high? Less or high? Guys, on the normal I'm asking in an electrical signal I'm calculating across the two terminal. If a voltage is very high, what will be the current? If voltage is low means what will be the current? For an open circuit, voltage is high or current is high? You tell me. For open circuit,
Sir, current, sir.
In your open circuit, current is high.
Yes, sir.
Current is high, open circuit.
No, sir.
Electrical, you're studying electrical engineering.
Sir, it's a voltage, sir. Sorry, sir.
Voltage is high, two terminal. So there is a open path so that the current cannot able to pass from one terminal to another terminal. And if it is short circuited, voltage becomes zero, current become high. Okay, similar concept here also. Okay, if the transistor is on in the sense, it will make the current flow. So if current flow is occurring means what will be the voltage? Voltage will be very less, right? According to the Ohm's law, V is equal to IR. Keep the resistance constant. If current is maximum, what will be your voltage? If current is maximum, what will be your voltage? Guys, same like open circuit and closed circuit. Now it is made as closed circuit. So closed circuit means the current is flowing, but the voltage is become less. Okay, once it is open circuit, I mean the transistor is not switch on. So switch on in the sense it is not, it is in off condition. It is not switch on means it is in off condition. On the time the base current is, there is no base current in order to drive the transistor. On the time there is no current flow, so output is will be your equal to your the voltage which is given to VCC. Is it right or not? Actually here I am giving a two biasing. One is a base biasing, another is a collector biasing. So collector biasing much more, 12 volt I will give. Base is based upon your input signal. I will give in terms of 1 millivolt, 2 millivolt. But your collector voltage is 12 volt. Suppose transistor is in on condition, on the time your output voltage is 0, current is maximum. If I am giving, I mean transistor is in on condition means current become higher, the voltage becomes 0. If transistor is in off condition, the voltage is higher, current is 0. So based upon that, the amplification will do. So suppose 1 milliamps I am flowing, on the time the collector to emitter current will be, for example, 100 milliamps. Suppose 2 milliamps is flowing based upon the amplitude level, which is I am giving input current. If you see the sinusoidal signal, if I am giving 0, the transistor is off. Off means output will be very higher. If I am slowly increasing the voltage, so voltage is rising means surely the current will rise. So based upon the resistance value, so current is also rising on the time transistor goes to on stage. So if it is going to on stage in the sense, it will make more current flow which is occurring from collector to emitter. Okay, so it representing short circuited. On the time the voltage becomes 0, current becomes maximum. Okay, and look at this, the current variation will be there. So base current is 1 milliamps means collector current will be 100 milliamps. For an example I am telling, if I improve much more, base current is 2 milliamps, so collector will flow 200 milliamps. If I am increasing to 3 milliamps, current collector current will flow 300 milliamps. For an example I am telling, typical value. Okay, if there is no current and output doesn't have any current, but voltage is maximum. How much voltage? It will be what is the voltage you are giving? 12 volt you are giving to the collector to emitter means that much voltage you may have. So the current amplification also happening here, and voltage amplification also happening here. So that's why I am preferring the common emitter configuration for maximum application. Do you guys understood this?
Yes, sir. Understand, sir.
So same thing here they are representing here. So look at this, they are talking about the current amplification. So during a positive off cycle, so positive I'm giving from 0 to maximum, maximum to minimum. So for a positive off cycle, input AC will keep the emitter base junction for more biasing. So more forward bias means transistor is in on condition. Okay, so that what will happen, so base is 1 milliamps is flowing, so that the collector to emitter current will be higher. So they are telling, so more carrier will be emitted by emitter, so this huge current will flow through load, and we will find output amplified signal. So we are talking about the current amplification. Okay, in this condition, the voltage will be less or high. Voltage will be less. And if you go for that during negative half cycle, input AC will keep the emitter base junction less forward bias. So less forward bias means it is in off condition. So on the time, so due to that off condition, there is no current flow. Very less current flow will there. So less carrier will be emitted by emitter. Hence collector current is decreased. So the collector current is flowing based upon your the base current. So base current is slowly increasing means collector current will increase rapidly. If the base current is reduced to less means the collector to emitter current is reduced. Okay. And similarly, I explained in voltage also. So voltage will be different. If I am giving more base current on the time, the output voltage will be higher. If it is less means the output voltage will be change. Okay. And this is no need. So up to this configuration is completed. So totally 3 configuration. Guys, any doubt in 3 types of configuration? Common base, common emitter, and common collector. Any doubt is there? See, for a common collector also, you wanna draw the input and output characteristics, which will be similar. Abhinav, what happened? Mic problem.